Hi guys! Tonight, we're embarking on a journey through time to explore one of humanity's most enduring architectural achievements, the medieval castle. These magnificent stone fortresses that dot the landscapes of Europe and beyond represent centuries of human ingenuity, determination, and craftsmanship. From the selection of the perfect hilltop location to the final placement of the weather vane atop the highest tower, castle construction was a monumental undertaking that could span decades and involve hundreds of skilled workers. We'll walk through every painstaking step of this incredible process, from the initial surveying of land to the intricate stonework that has withstood centuries of weather, conflict, and time itself. Tonight's story will take us deep into the world of medieval engineers, master masons, carpenters, and countless laborers who transformed raw materials into some of the most impressive structures ever built by human hands. Okay, friends, before you settle in, if you enjoy this kind of deep dive content, then click the like button and don't forget to subscribe. And yes, leave a comment letting me know where you're watching from and what time it is there. I really enjoy seeing where everyone is listening from. Now, dim the lights and turn on the fan, and let's dive into tonight's journey together. The story of how castles were built begins not with the first stone laid or the first timber hewn, but with a careful eye scanning the horizon for the perfect location. Medieval engineers and military strategists understood that the success of any fortress depended first and foremost on its placement in the landscape. They would spend months, sometimes years, evaluating potential sites with the precision of modern urban planners, but with tools and knowledge passed down through generations of builders. The ideal castle location required a delicate balance of strategic advantage, natural defense, and practical accessibility. A hilltop or elevated plateau provided the most obvious benefits, commanding views of the surrounding countryside that could extend for miles in every direction, making it nearly impossible for enemies to approach undetected. These elevated positions also offered natural drainage, preventing the accumulation of water that could weaken foundations or create unsanitary conditions within the castle walls. The process of evaluating potential sites often took months of careful observation and analysis. Master builders would visit prospective locations during different seasons to understand how weather patterns affected the terrain, how water flowed during spring melts and autumn rains, and how winter conditions might impact both construction activities and the eventual defensive capabilities of the fortress. They observed wind patterns that could affect the operation of siege engines or the spread of fire, noting prevailing directions and seasonal variations that could influence military tactics. Geographic features surrounding potential castle sites received intense scrutiny from military strategists and construction experts working together to evaluate both immediate and long-term implications of location choices. Natural barriers such as rivers, ravines, marshes, or dense forests could provide additional defensive advantages that would reduce the need for constructed fortifications while also potentially limiting access routes that enemies might use for approach or siege operations. These natural features could also influence the design and layout of the castle itself, as builders learned to incorporate existing terrain features into their defensive strategies. The evaluation process also considered the political and economic context of potential castle locations. Sites needed to be positioned to control important trade routes, river crossings, mountain passes, or other strategic points that would provide economic benefits and political influence for the castle's owner. The ability to collect tolls, monitor merchant traffic, and control access to valuable resources could provide ongoing income that would support the castle's operations and justify the enormous investment required for construction. Soil analysis techniques used by medieval builders might seem primitive by modern standards, but they were remarkably effective in the hands of experienced professionals who had learned to read the subtle signs that indicated suitable building conditions. Master builders would dig test holes at various points across a potential site, examining soil color, texture, moisture content, and the presence of organic materials that could indicate poor drainage or unstable conditions. They looked for signs of previous landslides, erosion, or other geological instability that could threaten a castle built on the site. Climate considerations played a crucial role in site selection decisions that would affect not only construction activities, but also the long-term habitability and defensive effectiveness of the completed castle. Builders needed to understand local weather patterns, including seasonal temperature variations, precipitation levels, prevailing wind directions, and the frequency and severity of storms that could affect construction work or damage completed structures. Sites that were too exposed to harsh weather could be difficult to defend and uncomfortable to inhabit, while locations that were too sheltered might lack the commanding views necessary for effective military surveillance. But elevation alone was not enough. The chosen site needed access to fresh water, either from a natural spring, a well that could be dug deep into the bedrock, or a river or stream that could be reliably accessed even during times of siege. Water was not just essential for drinking and cooking, but also for the countless construction activities that would take place over the years of building. Mortar needed to be mixed, stones needed to be cleaned, and the army of workers required constant hydration during their laborious days. The geological composition of the chosen site required careful examination by master builders who had developed an almost supernatural ability to read the land. They would examine rock outcroppings, test soil composition by digging small exploratory holes, and observe how water moved across and through the terrain during different seasons. Bedrock close to the surface was ideal for supporting the enormous weight of stone walls that might rise 60 feet or more into the sky. Soft soil or areas prone to shifting would doom a castle before construction even began. Transportation access presented another crucial consideration that required careful planning and foresight. While defensive positioning often favored remote, difficult-to-reach locations, the practical realities of construction demanded reasonably accessible routes for bringing in massive quantities of stone, timber, iron, and other materials. These supply routes needed to be secure from enemy interference, but also practical for the ox-drawn carts and pack animals that would carry tons of materials up steep hillsides and across rough terrain. The development of supply routes often required significant infrastructure investment that began long before actual castle construction commenced.
Existing roads might need to be widened, strengthened, or rerouted to handle the heavy traffic and enormous loads associated with castle construction. Bridges might require reconstruction or reinforcement to support loaded carts carrying multi-ton stone blocks. River crossings could necessitate the construction of specialized ferries or temporary bridges designed specifically to handle construction materials and equipment. Route planning also needed to consider security implications during both construction and operational phases of the castle's existence. Supply routes that were too exposed or predictable could be targeted by enemies seeking to disrupt construction activities or later siege operations. Alternative routes needed to be identified and developed to ensure continued access even if primary supply lines were compromised. The strategic value of controlling these transportation corridors often influenced the final selection of castle locations. Seasonal accessibility represented another critical factor in transportation planning that could significantly impact construction schedules and costs. Routes that were passable during dry summer months might become impassable during winter snow or spring mud seasons, forcing construction activities to be scheduled around weather patterns and requiring extensive stockpiling of materials during favorable transportation periods. Understanding these seasonal limitations was essential for developing realistic construction timelines and resource management strategies. The logistics of coordinating multiple transportation routes simultaneously required sophisticated planning and management capabilities that demonstrated the advanced organizational skills of medieval construction professionals. Different materials might arrive from various sources using different transportation methods, requiring careful scheduling to ensure that materials arrived at the construction site in the proper sequence and quantities needed for efficient construction progress. Stone from quarries, timber from forests, iron from forges, and specialized materials from distant suppliers all needed to be coordinated into a comprehensive supply system that could operate reliably over the years required for castle completion. Local availability of construction materials could make the difference between a project that took 5 years and one that stretched across decades. Quarries within a reasonable distance provided stone that matched the local geological conditions and required less transportation. Forests supplied timber for scaffolding, interior construction, and the countless wooden components that supported the building process. Clay deposits enabled the creation of bricks and roof tiles on site, rather than importing these heavy materials from distant locations. The assessment of local material resources required detailed surveys that could take months to complete thoroughly. Teams of specialists would fan out across the surrounding countryside, examining rock outcroppings to determine the quality and quantity of stone available from potential quarry sites. They would test stone samples for hardness, durability, and workability, often by actually cutting and shaping small pieces to understand how the material would behave under construction conditions. Forest surveys determined the species, sizes, and quantities of timber available, with particular attention to finding trees suitable for the long, straight beams needed for floor and roof construction. Clay and sand deposits received careful evaluation for their suitability in mortar production, brickmaking, and other construction applications. The quality of local clay could significantly impact the durability and weather resistance of mortar joints. while the availability of suitable sand affected both mortar quality and construction costs. Teams would dig test pits at various locations to understand the extent and quality of these deposits, often discovering valuable resources that had been overlooked by local inhabitants who lacked the specialized knowledge needed to evaluate construction materials. Water resources for construction received special attention beyond just the supply needs of the completed castle. Construction activities required enormous quantities of water for mortar mixing, stone cleaning, tool maintenance, and the daily needs of hundreds of workers. The location and capacity of water sources needed to support both construction activities and the eventual operational requirements of the completed castle. Springs, streams, and potential well sites were evaluated for their reliability, quality, and accessibility under various seasonal conditions. The evaluation of potential material suppliers and contractors required understanding of local economic conditions, craft capabilities, and political relationships that could affect the reliability and cost of construction resources. Master builders would meet with local quarry owners, timber suppliers, and craft specialists to negotiate contracts and assess their capability to meet the demanding requirements of castle construction. These negotiations often involved complex arrangements for payment, delivery schedules, and quality standards that would govern relationships throughout the construction period. Regional political conditions could significantly impact material availability and transportation security, requiring careful evaluation of relationships between local lords, trade agreements, and potential sources of conflict that could disrupt construction activities. Areas experiencing political instability might offer lower material costs, but at the risk of supply interruptions that could halt construction progress. The evaluation process needed to balance cost considerations against reliability and security factors that could affect project success. Labor availability represented another critical resource that required careful assessment during the site selection and planning phases. Castle construction required large numbers of both skilled craftsmen and general laborers, often exceeding the available workforce in local communities. Master builders needed to understand regional labor markets, seasonal availability patterns, and the potential for recruiting workers from distant areas to supplement local workforce capabilities. Skilled craftsmen, including stonemasons, carpenters, metalworkers, and specialists in various construction trades, were often in short supply and high demand throughout medieval Europe. The availability of these specialists could significantly impact both construction schedules and costs, making it essential to identify and secure commitments from qualified craftsmen early in the planning process. Master builders often maintained networks of contacts with skilled workers from previous projects, but major castle construction still required recruiting additional specialists from across wide geographic areas. General laborers for material handling, excavation, and other physically demanding tasks were typically recruited from local communities, but major projects often required workforce levels that exceeded local availability. Seasonal agricultural patterns affected the availability of rural workers who might be available for construction work during certain times of year, but needed to return to farming activities during planting and harvest seasons. Understanding these patterns was essential for developing realistic construction schedules and workforce planning strategies. Once the perfect location had been identified and secured, the next phase involved detailed surveying and planning that would establish the foundation for years of construction work.
Medieval surveyors, working with tools that seem primitive by modern standards but were remarkably effective in skilled hands, would map every contour of the chosen site with painstaking precision.
The surveyor's primary tools included the groma, a wooden cross with plumb lines hanging from each arm that allowed for establishing right angles and straight lines across uneven terrain. The corabates, a long wooden beam with perpendicular supports and a water channel or hanging plumb lines, helped establish level surfaces and consistent grades across the construction site. Simple but effective measuring chains and rods, often calibrated to local units of measurement that varied from region to region, enabled the precise layout of walls, towers, and interior spaces.
These surveying activities created the first detailed maps of the construction site, showing not only the planned locations of major structures, but also the drainage patterns, soil conditions, and elevation changes that would influence every aspect of the building process. Master builders would study these surveys for weeks, making adjustments to their plans based on the specific characteristics of the terrain and the strategic requirements of the fortress. The planning process involved far more than just architectural drawings. Master builders needed to estimate the quantities of materials required for each phase of construction, plan the sequence of building activities to maximize efficiency and minimize risks, and coordinate the complex logistics of feeding, housing, and organizing hundreds of workers over periods that could stretch across decades. Material calculations required extraordinary precision and foresight. A single castle might require tens of thousands of tons of stone, thousands of trees for timber, hundreds of tons of iron for reinforcement and hardware, and countless loads of sand, clay, and other materials for mortar and specialized construction needs. Underestimating these requirements could halt construction for months while additional materials were quarried, transported, and prepared. Overestimating led to waste and unnecessary expense that could strain the resources of even wealthy lords. The complexity of material calculations increased dramatically when considering the different types and grades of materials needed for various construction applications. Foundation work required different stone characteristics than wall construction, which differed from the requirements for decorative elements or defensive features. Master builders needed to understand these distinctions and calculate requirements for each type separately, while also considering how construction sequencing would affect material delivery and storage requirements. Stone calculations involved not just total quantities, but also specific sizes and shapes needed for different construction applications. Cornerstones required different dimensions than wall stones, while arch construction needed precisely shaped voussoirs cut to exact specifications. Window and door openings required specially sized and shaped stones, while defensive features like arrow loops and murder holes needed their own specialized stone components. Each of these requirements needed to be calculated separately and coordinated into comprehensive material orders. Timber calculations presented similar complexity challenges, with different species and sizes needed for various applications throughout the castle construction project. Scaffolding required enormous quantities of straight poles and planks that could be reused throughout the construction process, while interior construction needed beams sized for specific load-bearing requirements.
Roof construction required rafters, purlins, and other specialized timber components cut to precise dimensions for proper fit and structural performance. The calculation of hardware requirements involved detailed analysis of every door, window, gate, and mechanical system that would be incorporated into the castle design. Each door required hinges, locks, handles, and reinforcing hardware fabricated to specific requirements based on the size and security needs of the opening. Windows needed specialized hardware for operation and security, while gates and defensive systems required complex mechanical components that might need to be custom designed and fabricated for specific applications. Mortar calculations required understanding of the different formulations needed for various construction applications, along with the raw materials needed to produce adequate quantities of each type. Foundation mortar used different proportions of lime, sand, and additives than wall mortar, while pointing mortar for finishing joints required still different formulations. The calculation process needed to account for these variations while also considering factors like waste, weather delays, and quality control requirements that could affect actual consumption rates. Quality specifications for materials required detailed documentation that would guide procurement activities and ensure consistent standards throughout the construction process. These specifications covered not just basic material properties, but also dimensions, surface finishes, and performance requirements that would ensure compatibility with construction methods and long-term durability requirements. Master builders often maintained written specifications that could be shared with suppliers and used for quality control inspections upon material delivery. Delivery scheduling for materials required sophisticated coordination to ensure that materials arrived at construction sites when needed, without creating storage problems or interfering with ongoing construction activities. The scheduling process needed to consider transportation times, seasonal accessibility, supplier capabilities, and construction sequencing to create realistic delivery schedules that would support efficient construction progress while minimizing storage requirements and material handling costs. Material storage and handling systems required careful planning to manage the enormous quantities of materials that would accumulate at construction sites over the months and years of active construction. Stone stockpiles needed to be organized by type and size to facilitate efficient retrieval during construction activities, while also being positioned to minimize handling and transportation within the construction site. Timber storage required protection from weather and pests while maintaining accessibility for construction use. Security for stored materials represented an ongoing concern that required both physical security measures and administrative controls to prevent theft or unauthorized use of valuable construction materials. Stone and timber stockpiles were vulnerable to theft by local communities who could use these materials for their own construction needs, while metal components and tools were valuable enough to attract organized theft operations. Security measures needed to balance protection requirements against the need for convenient access by authorized construction workers. The sequence of construction activities followed patterns that had been refined through centuries of castle building experience. Certain tasks needed to be completed before others could begin, creating complex interdependencies that required careful coordination. Foundation work had to be finished before walls could rise,
But quarrying and material preparation could begin long before the site was fully prepared. Skilled craftsmen needed to be engaged and scheduled to arrive at precisely the right moments in the construction timeline. With surveying complete and plans finalized, the actual construction work could begin, with the most critical and labor-intensive phase of the entire project, the excavation and preparation of foundations. Medieval builders understood that the strength and longevity of their massive stone structures depended absolutely on foundations that could distribute enormous weights evenly and resist the freeze-thaw cycles, ground settlement, and seismic movements that could destroy years of work in a matter of moments. Foundation excavation began with the careful removal of topsoil, organic matter, and any loose materials that could compress or decompose over time. Workers used shovels, picks, and wooden implements to dig trenches that followed the planned outline of walls and towers, often reaching depths of 6 to 12 feet or more, depending on local soil conditions and the height of the planned structures. The organization of excavation work required careful planning to manage the enormous quantities of soil and rock that would be removed from foundation trenches. A typical castle foundation system might require the excavation and removal of thousands of cubic yards of material, all of which needed to be moved using human labor and simple tools. Work crews were organized into specialized teams responsible for digging, loading excavated material onto carts or carrying baskets, and transporting the material to designated disposal areas that would not interfere with ongoing construction activities. Excavation techniques varied depending on the soil and rock conditions encountered at different locations within the construction site. Soft soils could be removed relatively quickly using shovels and picks, but rocky areas might require more intensive techniques, including the use of wedges, levers, and controlled heating and cooling methods to break up solid rock formations. Workers developed specialized skills in reading soil and rock conditions, allowing them to select the most appropriate tools and techniques for efficient excavation under varying conditions. The disposal of excavated materials presented logistical challenges that required careful planning and ongoing management throughout the excavation phase. Some excavated soil could be used for other construction purposes, such as creating berms or filling low areas around the castle site. But much of the material needed to be transported to disposal areas that would not interfere with construction activities or create drainage problems. The location of disposal areas needed to be planned carefully to avoid creating artificial hills or depressions that could provide cover for attacking forces or interfere with the defensive capabilities of the completed castle. Excavation work was typically organized around seasonal patterns that took advantage of favorable weather conditions while avoiding periods when frozen ground, excessive moisture, or other environmental factors would make digging difficult or impossible. The timing of excavation activities also needed to be coordinated with the availability of skilled workers and the delivery schedules for materials that would be needed for foundation construction. Delays in excavation could cascade through the entire construction schedule, making careful planning and execution essential for project success. Safety considerations during excavation work required constant attention to prevent accidents that could injure workers or delay construction progress. Deep trenches posed risks of cave-ins that could trap or injure workers,
requiring the use of timber shoring systems to support trench walls during excavation and foundation construction activities. Drainage systems needed to be maintained to prevent water accumulation in trenches that could create unsafe working conditions or undermine the stability of excavation walls.
The precision required for foundation excavation went far beyond simple hole digging, requiring careful attention to exact dimensions, angles, and elevations that would ensure proper construction of the foundation walls and supporting structures. Workers used string lines, measuring rods, and other simple tools to maintain accurate trench dimensions and ensure that foundation walls would be built in exactly the planned locations and orientations. Even small errors in excavation dimensions could create problems that would persist throughout the construction process. The excavation work revealed the true character of the building site and sometimes forced modifications to the original plans. Unexpected rock formations might require changes to the layout of walls or towers. Underground springs could necessitate additional drainage work or even relocation of entire sections of the castle. Soil conditions that differed from initial estimates might require deeper foundations or additional reinforcement. Unexpected archaeological discoveries during excavation could provide valuable insights into previous use of construction sites while also potentially affecting construction plans and schedules. Evidence of earlier structures, burial sites, or other human activity required careful documentation and sometimes consultation with religious authorities or local officials before construction could proceed. These discoveries occasionally led to significant changes in castle layout or construction methods to accommodate archaeological or religious considerations. Rock formations encountered during excavation varied dramatically in their impact on construction activities and costs. Solid bedrock near the surface provided excellent foundation support, but could require expensive and time-consuming removal to achieve proper foundation depths and configurations. Fractured or layered rock formations might provide adequate support while being easier to excavate, but could also present drainage challenges that required additional engineering solutions. Underground water conditions discovered during excavation often differed significantly from surface observations and could require major modifications to foundation design and construction methods. High water tables could necessitate deeper drainage systems or even relocation of planned structures to higher ground. Spring discoveries sometimes provided unexpected water supply opportunities, but could also create drainage challenges that required specialized engineering solutions. Soil contamination from previous activities on construction sites occasionally presented challenges that required remediation before foundation construction could proceed safely. Areas that had been used for metalworking, animal processing, or waste disposal might contain materials that could affect construction quality or worker health. The identification and treatment of these conditions required specialized knowledge and sometimes delayed construction while appropriate remediation measures were implemented. The discovery of valuable materials during excavation occasionally provided unexpected benefits that could offset construction costs or provide additional resources for the project. Deposits of clay suitable for brick or tile production could reduce material procurement costs while also providing business opportunities for the castle owner. Mineral deposits, or stone formations of unusual quality, might provide materials for decorative elements, or could be marketed to other construction projects in the region. Excavation in areas with complex geology required specialized techniques and expertise that went beyond simple digging and material removal. Layered soil formations needed to be excavated using methods that maintained stability while achieving required depths and configurations. Geological formations that were prone to shifting or collapse required temporary support systems during excavation and special techniques for foundation construction. Weather impacts on excavation work required flexible scheduling and adaptive techniques that could maintain progress despite challenging environmental conditions. Heavy rains could flood excavation areas and delay work for days or weeks, while also potentially undermining the stability of excavated areas. Frozen ground conditions during winter months could make excavation extremely difficult or impossible, requiring careful timing of excavation activities to take advantage of favorable weather periods. The coordination of excavation work with other construction activities required careful scheduling to ensure that excavation proceeded ahead of foundation construction while not interfering with material delivery, storage, or preparation activities. Excavation equipment and crews needed access to work areas while also allowing continued operation of quarrying, stone cutting, and other preparation activities that were proceeding simultaneously throughout the construction site. Waste management during excavation required systems for sorting, transporting, and disposing of different types of excavated materials in ways that would not interfere with ongoing construction activities or create environmental problems. Topsoil and organic materials needed different handling than rock and clay, with some materials potentially useful for landscaping or other construction applications, while others required disposal in designated areas away from the construction site. As excavation proceeded, workers paid careful attention to the precise leveling and alignment of foundation trenches. The groma and other surveying tools were used constantly to ensure that walls would meet at perfect right angles and that the finished structure would have the geometric precision required for both structural integrity and defensive effectiveness. Even small errors in foundation layout could propagate upward through the entire structure, creating weak points that could be exploited by attackers or that could lead to structural failures. The bottom of foundation trenches required special preparation that went far beyond simple digging. Workers would compact the soil by repeatedly pounding it with heavy wooden implements, creating a firm base that would not settle unevenly under the enormous loads it would need to support. In areas with questionable soil conditions, builders might drive wooden stakes deep into the ground to create additional support, or they might excavate even deeper to reach bedrock or more stable soil layers. Drainage considerations were absolutely critical in foundation preparation. Medieval builders understood that water infiltration could undermine foundations through frost action, soil erosion, or the gradual weakening of mortar joints. They incorporated drainage systems directly into foundation design, creating channels and pipes that would direct water away from vulnerable areas and prevent the accumulation of moisture that could cause long-term damage. The foundation walls themselves were built using construction techniques that had been developed and refined through centuries of experience with large stone structures. The first courses of stone were the largest and heaviest that the builders could manage, creating a stable base that would resist shifting and provide a level platform for the walls above.
These foundation stones were often laid directly on bedrock when possible, or on carefully prepared beds of compacted gravel and sand that would distribute loads evenly. Mortar for foundation work required special formulations that would remain stable in the damp conditions typically found below ground level. Medieval builders developed mortars using lime, sand, and water, but they often added special ingredients like crushed pottery, ground brick, or even animal blood to improve water resistance and adhesion properties. The lime itself was produced on site using limestone and wood fuel, a process that required considerable expertise to produce consistent results.
The laying of foundation stones followed precise patterns that ensured maximum strength and stability. Stones were fitted together with minimal gaps, and mortar was applied evenly to create joints that would distribute loads effectively.
The builders paid special attention to corner construction, where walls met at angles that required careful cutting and fitting of stones to create strong connections that would resist the enormous stresses imposed by the weight of walls and towers above. As foundation walls rose above ground level, builders began to incorporate the complex systems of passages, chambers, and openings that would serve various functions throughout the life of the castle. Drainage channels were built into the walls themselves, often lined with carefully fitted stones that would resist erosion and blockage. Ventilation systems were incorporated to prevent moisture buildup in foundation areas that could lead to structural problems or create unhealthy conditions in lower levels of the castle. With foundations complete and properly cured, construction could move to the next major phase: the quarrying, transportation, and preparation of the enormous quantities of stone that would form the walls, towers, and other major structural elements of the castle. This phase of construction required the coordination of quarrying operations, transportation systems, and on-site stone preparation activities that would continue throughout the years-long construction process. The selection of appropriate stone for castle construction required expertise that combined geological knowledge, engineering experience, and practical understanding of how different stone types would perform under the specific conditions they would encounter. Builders preferred stones that were hard enough to resist weathering and strong enough to support enormous loads, but soft enough to be cut and shaped with the tools available to medieval craftsmen. Stone selection involved detailed analysis of potential quarry sites that could provide adequate quantities of suitable material within reasonable transportation distance of the construction site. Master builders and experienced stonemasons would visit multiple quarries, examining rock formations for consistency, quality, and workability characteristics that would meet the specific requirements of different parts of the castle construction project. They looked for stone beds that were free of cracks, inclusions, and other flaws that could weaken finished construction or create difficulties during cutting and shaping operations. The testing of stone quality involved techniques that had been developed through generations of experience with different types of rock and their performance in construction applications. Stonemasons would extract sample blocks from potential quarry sites and subject them to various tests, including resistance to weathering, ease of cutting and shaping, and structural strength under load. These tests helped ensure that selected stones would meet the demanding requirements of castle construction while also being workable with available tools and techniques. Different types of stone were often selected for different applications within a single castle project.
taking advantage of the specific characteristics that made each type suitable for particular uses. The hardest, most weather-resistant stones might be reserved for exterior surfaces that would be exposed to the elements, while softer, more easily worked stones could be used for interior construction, where weather resistance was less critical, but ease of cutting and fitting was more important. Decorative elements might require stones with fine grain structure that could be carved with intricate detail, while structural elements needed stones with superior load-bearing capabilities. Regional variations in available stone types influenced both the appearance and construction techniques used in different castle projects. Castles built in limestone regions typically had a light-colored appearance and used construction techniques optimized for working with relatively soft, easily cut stone. Granite regions produced darker, more rugged-appearing castles that required different tools and techniques for stone cutting and fitting. Sandstone regions offered stones with intermediate characteristics that provided good workability combined with reasonable weather resistance. The economic factors involved in stone selection often required careful balancing of material costs, transportation expenses, and performance requirements. Higher quality stones from distant quarries might provide superior performance, but at costs that could significantly impact project budgets and timelines. Local stones of somewhat lower quality might be perfectly adequate for many applications, while providing significant cost savings that could be applied to other aspects of the construction project. Quality control systems for stone selection and procurement required ongoing attention throughout the construction process to ensure that delivered materials met specifications and quality standards. Stone deliveries were inspected upon arrival at the construction site, with defective or unsuitable materials rejected and returned to suppliers. This quality control process helped maintain construction standards while also providing feedback to quarry operations that could improve their selection and preparation processes. Limestone was often the preferred choice for castle construction because it offered an excellent balance of workability and durability. It could be cut relatively easily when first quarried, but would harden and become more weather-resistant after exposure to air. Sandstone provided another excellent option, particularly varieties that had fine, consistent grain structure and good compressive strength. Granite and other igneous rocks offered superior durability but required much more labor to quarry and shape. The quarrying process began with the careful examination of potential stone sources to identify layers and blocks that would provide the sizes and shapes needed for castle construction. Quarrymen developed remarkable skills in reading the natural fracture patterns and grain structure of rock formations, allowing them to extract blocks with minimal waste and maximum efficiency. They used a combination of techniques, including wedging, heating and cooling, and careful percussion to separate blocks from the living rock. Wedging techniques involved drilling or chiseling narrow slots into the rock along natural fracture lines, then driving wooden or iron wedges into these openings to create controlled splits. The wooden wedges were sometimes soaked with water to make them expand slowly and create steady pressure that would separate stones along predictable lines. Iron wedges could be driven with sledgehammers to create more immediate splitting action when the stone characteristics were appropriate. Heating and cooling methods took advantage of the expansion and contraction of rock under temperature changes.
Quarrymen would build fires directly on rock surfaces, then douse the heated stone with cold water to create thermal shock that would open fractures along weak points in the rock structure. This technique required considerable experience to control effectively and was not suitable for all types of stone. Once blocks were separated from the quarry face, they required rough shaping and sizing to make them suitable for transportation and final preparation at the construction site. Quarrymen used heavy chisels, hammers, and other stoneworking tools to remove irregularities and create blocks that approximated the dimensions needed for specific construction purposes. This rough preparation reduced transportation costs and made the final shaping process more efficient. The techniques used for rough shaping at quarry sites required considerable skill to balance efficiency with quality considerations that would affect subsequent finishing work. Experienced quarrymen could remove excess material quickly while preserving the maximum usable volume from each rough block. They understood how different stone types responded to various cutting techniques and could adjust their methods to achieve optimal results with minimal waste and effort. Quality control during quarry operations required ongoing inspection and testing to ensure that extracted stones would meet the demanding requirements of castle construction. Quarrymen developed the ability to identify potential flaws and weaknesses in stone that could cause problems during cutting, transportation, or final installation in castle walls. Stones with suspected problems were often rejected at the quarry site to avoid the costs and delays associated with transporting defective materials to construction sites. The organization of quarry operations required coordination of multiple work crews performing different aspects of the extraction and preparation process. Crews responsible for initial rock breaking worked alongside teams performing rough shaping and sizing operations, while other workers handled material movement and loading for transportation. This coordination required experienced supervision and careful scheduling to maintain efficient production while ensuring worker safety in the dangerous environment of active quarry operations. Quarry site development required significant infrastructure investment that might continue throughout the construction period as extraction operations moved to different areas within quarry sites. Access roads needed to be built and maintained to handle heavy loaded carts, while working areas required ongoing development as extraction proceeded deeper into rock formations or expanded to new areas of the quarry site. Water management systems prevented flooding of working areas while providing the water needed for stone cutting and cleaning operations. Environmental considerations in quarry operations included managing the impacts of extraction activities on surrounding areas and communities. Quarry operations could affect local water systems, create noise and dust problems for nearby residents, and require disposal of waste materials that were not suitable for construction use. Master builders needed to balance efficient extraction operations with community relations and environmental stewardship that would support long-term construction success. The economics of quarry operations required careful analysis of extraction costs, transportation expenses, and quality considerations to ensure that stone production could meet castle construction requirements within reasonable cost parameters. Quarry site selection needed to balance proximity to construction sites against stone quality and availability considerations that would affect both immediate costs and long-term construction success. Seasonal patterns in quarry operations reflected both weather conditions that affected extraction activities and transportation limitations that influenced delivery schedules. Winter quarrying was often limited by frozen conditions that made extraction difficult and transportation unreliable, requiring careful stockpiling of materials during favorable weather periods to maintain construction supplies throughout the year. Worker housing and support systems at quarry sites provided the infrastructure needed to maintain stable workforces throughout the extended periods required for major castle construction projects. Quarry operations might continue for years or decades, requiring permanent or semi-permanent facilities that could house workers and their families while providing the stability needed for efficient operations and quality production. Tool and equipment maintenance at quarry sites required specialized facilities and expertise to keep extraction and stoneworking equipment in proper condition throughout intensive use periods. The harsh conditions of quarry work caused rapid wear of tools and equipment, requiring ongoing maintenance and replacement activities that needed to be planned and managed as integral parts of quarry operations. Safety considerations in quarry operations required constant attention to prevent accidents and injuries that could affect both individual workers and overall production capabilities. The inherent dangers of working with heavy materials, sharp tools, and unstable rock formations required specialized safety procedures and protective equipment that were constantly evolving as experience revealed new risks and better protection methods. Transportation of stone from quarry to construction site represented one of the most challenging logistical aspects of castle construction. Individual blocks might weigh several tons, and the total quantity of stone required could reach tens of thousands of tons for a major castle project. Medieval transportation systems relied primarily on human and animal power, using ox-drawn carts, sleds, and specialized hauling equipment designed specifically for moving heavy stone blocks. The design and construction of transportation routes required careful engineering to handle the enormous loads involved in castle construction. Roads needed to be properly graded to prevent carts from becoming stuck or overturning on steep grades. Bridges required reinforcement to support the weight of loaded stone carts. River crossings might require the construction of special ferries or temporary bridges designed specifically for construction traffic. Ox-drawn carts were the primary means of stone transportation over moderate distances on reasonably level terrain. These specialized carts featured heavy wooden wheels, reinforced axles, and loading beds designed to carry and secure large stone blocks. A typical cart might carry 1 to 3 tons of stone, depending on the size of the blocks and the capacity of the oxen. Teams of 4, 6, or even 8 oxen might be required to move fully loaded carts over difficult terrain. For transportation over longer distances or particularly difficult terrain, builders sometimes used water routes when available. Barges and boats could carry much heavier loads than wheeled vehicles and could navigate rivers and coastal waters to deliver stone directly to construction sites. This water transportation required specialized loading and unloading facilities, but could significantly reduce the time and cost of moving materials over long distances. Water transportation systems required sophisticated engineering and logistics coordination that often involved multiple transportation modes and transfer points between different types of vessels.
Stone loaded onto river barges at quarry sites might need to be transferred to ocean-going vessels for coastal transport, then transferred again to smaller craft for final delivery to construction sites.
Each transfer point required specialized equipment and facilities for handling heavy stone blocks safely and efficiently.
The development of specialized vessels for stone transportation represented significant technological achievements that enabled castle construction projects to access high-quality materials from distant sources. Stone barges were designed with reinforced hulls and specialized loading equipment that could handle the concentrated loads and harsh handling conditions associated with heavy stone transport. These vessels often incorporated lifting equipment that could load and unload stone blocks without requiring elaborate shore-based facilities. River navigation for stone transport required detailed knowledge of seasonal water levels, navigational hazards, and channel characteristics that could affect the safe passage of heavily loaded vessels. River pilots with specialized knowledge of local conditions were often employed to guide stone barges through challenging passages and ensure safe delivery of valuable cargo. Seasonal variations in water levels could significantly affect transportation capacity and scheduling, requiring flexible logistics planning to accommodate changing conditions. Port and harbor facilities for stone transportation required specialized infrastructure that could handle the unique requirements of heavy stone cargoes while providing efficient transfer between water and land transportation systems. Loading and unloading facilities needed to accommodate the enormous weights of individual stone blocks while providing stable platforms for lifting equipment and worker safety. Storage areas at ports allowed for temporary stockpiling of materials when transportation schedules did not align perfectly with construction requirements. The economics of water transportation for castle construction materials often made distant, high-quality sources economically competitive with local materials of lesser quality. The lower transportation costs per ton achievable with water transport could offset the higher material costs of premium stones while providing access to specialized materials that were not available locally. This economic advantage enabled castle builders to specify higher quality materials that would provide superior long-term performance and appearance. Coordination between water and land transportation systems required sophisticated logistics planning that could accommodate the different scheduling, capacity, and handling characteristics of various transportation modes. Materials arriving by water transport needed to be efficiently transferred to land-based transportation for final delivery to construction sites, often requiring temporary storage and handling facilities at transfer points to buffer differences in transportation schedules and capacities. Weather impacts on water transportation required flexible scheduling and contingency planning that could maintain material delivery schedules despite seasonal and temporary weather-related disruptions. Storm conditions could halt water transport for days or weeks, requiring advanced stockpiling of critical materials to maintain construction progress during transportation disruptions. Ice conditions during winter months could completely halt river and coastal transport, requiring careful seasonal planning of material deliveries. Security considerations for water transportation included protection of valuable stone cargoes from theft, piracy, and political interference that could disrupt construction supply chains. Stone shipments represented significant value that could attract criminal attention, while political conflicts could affect access to transportation routes or ports needed for efficient material delivery. Security measures needed to balance protection requirements against cost and scheduling considerations. Insurance and risk management for water transportation of construction materials involved assessment and mitigation of risks, including vessel loss, cargo damage, and delivery delays that could significantly impact construction costs and schedules. The high value and specialized nature of construction stone made cargo loss particularly expensive, while delivery delays could halt construction progress and create expensive cascade effects throughout construction schedules. Sleds and rollers provided alternatives to wheeled transportation in certain situations. Heavy stone blocks could be loaded onto wooden sleds and dragged over prepared surfaces using teams of oxen or groups of workers. Wooden rollers placed under blocks or sleds could reduce friction and make it possible to move extremely heavy pieces with available power sources. These methods were particularly useful for moving stones over short distances or on construction sites where wheeled vehicles would have difficulty maneuvering. The arrival of stone at the construction site marked the beginning of another complex phase of material preparation and organization. Stones needed to be sorted by size, shape, and intended use, then stockpiled in locations that would facilitate efficient construction while keeping work areas clear and safe. Stone cutting and shaping activities required specialized work areas with proper drainage, tool storage, and waste removal systems. Master stone cutters and their assistants performed the precise shaping and finishing work that transformed rough quarry blocks into the carefully fitted pieces that would form castle walls and architectural details. This work required years of training and experience to develop the skills needed to cut stones to exact dimensions and create the complex shapes required for corners, openings, decorative elements, and specialized structural components. The tools used for stone cutting and shaping were relatively simple, but required great skill to use effectively. Chisels of various sizes and shapes were used for different types of cutting and detailing work. Mallets and hammers provided the percussion power needed to drive chisels through stone. Measuring devices, including squares, compasses, and templates, ensured that finished stones would fit properly into their intended positions in the castle walls. Stone cutting techniques varied depending on the type of stone being worked and the precision required for specific applications. Soft stones could be cut relatively quickly using broad chisels and steady percussion. Harder stones required more time and patience, with cutters using a series of progressively finer tools to achieve the desired shape and surface finish. Decorative elements required especially careful work, with master craftsmen spending days or weeks creating single pieces that would serve both structural and aesthetic functions. The development of specialized stone-cutting tools represented centuries of evolution in metalworking and tool design that enabled medieval craftsmen to achieve remarkable precision and efficiency in their work. Chisels were manufactured in dozens of different sizes and shapes, each optimized for specific types of cutting operations. Broad chisels were used for rough shaping and removal of large amounts of material, while narrow chisels allowed for precise detail work and the creation of fine surface textures. Pointed chisels could create holes and grooves, while flat chisels produced smooth, even surfaces. Tool maintenance represented a constant concern for stonecutters who depended on sharp, properly shaped tools for efficient and accurate work. Chisels required frequent sharpening, using whetstones and other abrasive materials to maintain the keen edges needed for clean cutting action. The tempering and heat treatment of steel tools required specialized knowledge to achieve the proper balance of hardness and durability that would allow tools to hold sharp edges while resisting damage from the repeated impacts of stone-cutting work. The techniques used for measuring and marking stones before cutting required precision and attention to detail that ensured finished pieces would fit properly into their intended positions in castle walls and structures. Master stonecutters used templates made from wood or metal to mark complex shapes and curves onto raw stone blocks, ensuring that multiple pieces would have consistent dimensions and profiles. Measuring devices, including squares, compasses, and calipers, allowed for precise measurement and verification of dimensions during cutting operations. Stone cutting work required physical techniques that maximized efficiency while minimizing fatigue during the long days of labor required to produce the thousands of finished stones needed for castle construction. Experienced stonecutters developed efficient body positions and striking techniques that allowed them to work steadily for hours without excessive strain or fatigue. They learned to read the grain structure of different stones and adjust their cutting techniques accordingly, working with natural fracture patterns to achieve desired results with minimum effort. The organization of stone cutting operations required coordination between rough cutting activities that produced approximately sized blocks and finish cutting that created precisely dimensioned pieces ready for installation in castle walls. Rough cutting could be performed at quarry sites to reduce transportation costs and volumes, while finish cutting typically took place at the construction site, where exact dimensions could be verified and adjusted as needed based on the actual construction progress and requirements. Apprenticeship systems in stone-cutting trades ensured the transmission of knowledge and skills from master craftsmen to new generations of workers who would continue the traditions and techniques that enabled castle construction. Young apprentices began with simple tasks like tool maintenance and material handling, gradually learning more complex skills through observation and practice under the guidance of experienced craftsmen. The development of expertise in stone cutting typically required years of training and experience to achieve the skill levels needed for the most demanding construction applications. Specialization within stone-cutting trades allowed individual craftsmen to develop particular expertise in specific types of work, such as architectural details, defensive features, or structural elements. Master carvers might specialize in decorative stonework that required artistic skills as well as technical knowledge, while other specialists focused on the production of precisely fitted structural stones that required different types of expertise and experience. The organization of stone-cutting activities required careful coordination with the overall construction schedule. Stones for foundation work needed to be prepared first, followed by stones for wall construction in the sequence that building would proceed. Specialized pieces like window frames, door jambs, and decorative elements needed to be completed in time for installation, but not so far in advance that they would be damaged or misplaced during the construction process. Quality control in stone preparation was absolutely critical to the success of the overall construction project. Stones that were cut incorrectly or that had flaws that were not detected during preparation could cause significant delays and additional expenses when discovered during wall construction. Master builders and experienced stonecutters inspected each finished piece to ensure that it met the specifications and quality standards required for its intended use. With adequate supplies of properly prepared stone available, construction could proceed to the actual building of castle walls, towers, and other major structural elements. This phase of construction required the coordination of multiple skilled trades, specialized equipment, and complex logistical systems that would operate simultaneously throughout the construction site for periods that could stretch across many years. The construction of castle walls followed techniques and patterns that had been developed and refined through centuries of experience with large stone structures. Walls were typically built with an outer face of carefully fitted stones, an inner face of similar construction, and a core of rubble and mortar that provided mass and structural integrity. This composite construction method provided the strength needed to support enormous loads while making efficient use of available materials and skilled labor. The outer faces of walls were constructed using stones that had been cut and shaped to precise dimensions, creating smooth surfaces that would resist weathering and provide an attractive appearance. These facing stones were typically the largest and highest quality stones available, and they were fitted together with thin mortar joints that provided structural continuity while minimizing the amount of mortar required. The quality of workmanship in wall faces was often a source of pride for master builders and a demonstration of their skills to potential future clients. Behind the facing stones, builders created a core of smaller stones, broken rock, and mortar that filled the space between the inner and outer wall faces. This rubble core provided the mass and structural stability needed to support the enormous loads imposed by towers, roofs, and defensive elements. The rubble was laid in layers with mortar between each course, creating a solid mass that would cure to become essentially a single monolithic structure. The construction process required careful attention to maintaining level courses and vertical alignment as walls rose higher. Builders used string lines, levels, and plumb lines to ensure that walls remained straight and properly aligned. Wooden frames and guides were often constructed to provide reference points for wall construction and to support scaffolding and lifting equipment needed to raise stones to working height. Scaffolding systems were essential for wall construction and required considerable expertise to design and build safely. Medieval builders used wooden poles, planks, and rope lashings to create scaffolding that could support workers, tools, and materials at heights that sometimes exceeded 60 feet. These scaffolding systems needed to be strong enough to handle heavy loads, but flexible enough to be adjusted and reconfigured as construction progressed. The design principles underlying medieval scaffolding systems demonstrated sophisticated understanding of structural engineering concepts that enabled builders to create temporary structures capable of supporting enormous loads safely and efficiently. Scaffolding needed to transfer the weights of workers, tools, and building materials down through multiple levels of temporary structure to stable foundations or bracing points that could handle these concentrated loads without failure.
The design process required careful analysis of load paths, connection details, and stability requirements that would ensure safe operation under all expected working conditions.
Construction of scaffolding systems typically began with the establishment of primary support posts that would carry the major loads and provide stable anchor points for the entire temporary structure. These posts needed to be properly sized for the loads they would carry and securely anchored to foundations, existing wall structures, or specially constructed footings that would prevent settling or shifting under load. The spacing and alignment of primary posts determined the overall geometry of the scaffolding system and influenced its load-carrying capacity and stability characteristics. Horizontal members, including ledgers, putlogs, and working platforms, created the framework that distributed loads between vertical supports while providing stable working surfaces for construction activities. These horizontal elements needed to be properly sized and spaced to handle the distributed loads of workers and materials while maintaining adequate stiffness to prevent excessive deflection that could create unsafe working conditions. The connections between horizontal and vertical members required special attention to ensure that loads were transferred efficiently while allowing for the adjustments and reconfigurations that were necessary as construction progressed. Bracing systems within scaffolding structures provided the lateral stability necessary to prevent collapse under wind loads, unbalanced loading, or other destabilizing forces that could occur during construction activities. Cross braces, diagonal members, and tiebacks to existing structures created triangulated frameworks that resisted lateral movement while maintaining the flexibility needed for ongoing construction work. The design and installation of bracing systems required understanding of structural stability principles that prevented scaffolding collapse under adverse conditions. Access systems, including ladders, ramps, and lifting points, needed to be integrated into scaffolding designs to provide safe and efficient means for workers and materials to reach different working levels. These access systems needed to be positioned for convenience and safety while avoiding interference with construction activities or compromising the structural integrity of the scaffolding system. The design of access systems also needed to consider the emergency evacuation requirements that would allow workers to exit scaffolding quickly in case of structural problems or other hazardous conditions. Material handling capabilities built into scaffolding systems enabled the efficient movement of stones, mortar, tools, and other construction materials to working levels where they would be needed for wall construction activities. Lifting points, material platforms, and temporary storage areas needed to be integrated into scaffolding designs without overloading the structure or creating safety hazards for workers. The positioning of material handling facilities needed to support efficient workflow while maintaining adequate working space for construction activities. Safety considerations in scaffolding design and construction required constant attention to details that could prevent accidents and injuries during the extended periods when these temporary structures would be in use. Guardrails, fall protection systems, and secure working surfaces helped protect workers from falls that could cause serious injury or death. Regular inspection and maintenance procedures ensured that scaffolding remained in safe condition throughout the construction period, with damaged or weakened components replaced before they could create hazardous conditions.
The disassembly and reconfiguration of scaffolding systems as construction progressed required careful planning to maintain safe working conditions while allowing construction activities to continue efficiently. Scaffolding typically needed to be adjusted or relocated multiple times during wall construction as work progressed upward and different areas of the construction required access and support. This ongoing modification work needed to be coordinated carefully with construction activities to avoid delays or safety problems. The lifting and positioning of stones at height required specialized equipment and techniques that demonstrated remarkable ingenuity. Builders used various types of cranes, winches, and pulley systems to raise heavy stones to their final positions in walls and towers. These lifting devices were typically constructed from wood and used human or animal power to provide the mechanical advantage needed to move heavy loads vertically. The design and construction of medieval lifting equipment represented sophisticated understanding of mechanical principles that enabled builders to achieve remarkable lifting capabilities using relatively simple materials and power sources. Crane designs incorporated lever systems, gear trains, and pulley arrangements that could multiply human or animal power to lift loads weighing several tons to heights exceeding 60 feet. These mechanical systems required careful design and construction to ensure safe, reliable operation under the demanding conditions of castle construction. Treadwheel cranes represented the most sophisticated and powerful lifting equipment used in medieval construction, incorporating large wooden wheels that workers could operate by walking inside the wheel circumference. These human-powered systems could generate steady, controllable lifting power that was well-suited to the precision requirements of stone positioning in castle walls. The treadwheel design allowed multiple workers to contribute power simultaneously, while providing excellent control over lifting speed and positioning accuracy. The construction of treadwheel cranes required specialized carpentry skills and understanding of mechanical engineering principles that enabled these complex machines to operate safely and efficiently under demanding construction conditions. The wooden wheels needed to be perfectly balanced and securely constructed to handle the enormous loads and dynamic forces generated during lifting operations. Gear systems and brake mechanisms provided speed control and safety features that prevented accidents during critical lifting operations. Positioning and anchoring systems for construction cranes required careful engineering to ensure stability and safety during lifting operations that imposed enormous loads and overturning moments on crane structures. Crane bases needed to be securely anchored to foundations or ballasted with stone or other heavy materials to prevent tipping during maximum load conditions. Guide systems and stabilizing features prevented crane movement that could cause accidents or damage to partially completed construction. Counterweight systems in some crane designs provided additional lifting capacity while also improving operational control and safety during stone positioning operations. These systems used heavy stone or metal weights to balance lifting loads and reduce the human power required for lifting operations. Counterweight systems required careful calculation and adjustment to optimize lifting performance while maintaining safe operation under varying load conditions. Winch and pulley systems provided simpler alternatives to complex crane designs for applications where lifting requirements were less demanding or where space constraints prevented the use of larger lifting equipment. These systems could be quickly set up and repositioned as construction progressed, providing flexibility and efficiency for smaller lifting tasks throughout the construction site.
Multiple pulley arrangements provided mechanical advantage that enabled workers to lift loads much heavier than would be possible with simple manual lifting. The operation of lifting equipment required specialized skills and experience that were essential for safe, efficient construction progress. Crane operators needed to understand load limitations, operational procedures, and safety requirements that would prevent accidents and equipment damage during critical construction activities. The coordination between crane operators, signal personnel, and construction workers required clear communication and standardized procedures that ensured safe operation in the complex, busy environment of active construction sites. Maintenance and repair of construction lifting equipment required ongoing attention throughout the extended construction periods typical of castle projects. The demanding conditions of construction use caused wear and damage that needed to be identified and corrected before equipment failure could cause accidents or construction delays. Maintenance activities included regular inspection, lubrication, replacement of worn components, and structural repairs that maintained equipment in safe, reliable operating condition. Safety procedures for lifting operations evolved through experience and became increasingly sophisticated as builders learned to identify and prevent the various types of accidents that could occur during stone lifting and positioning activities. Safety measures included inspection procedures, load limitation systems, worker positioning protocols, and emergency procedures that protected workers and equipment from the inherent dangers of heavy lifting operations at considerable heights. Treadwheel cranes represented one of the most sophisticated lifting devices used in castle construction. These machines used a large wooden wheel that workers could walk inside, similar to a hamster wheel, to provide steady rotational power that could be transmitted through gear systems to lifting drums and cables. A single treadwheel crane operated by 2 or 3 workers could lift loads of several tons to considerable heights with good control and safety. Mortar preparation and application represented another critical aspect of wall construction that required specialized knowledge and careful attention to quality control. Medieval builders understood that mortar served not just as an adhesive to hold stones together, but as a structural component that needed to distribute loads evenly and resist weathering, freeze-thaw cycles, and other environmental stresses. The preparation of lime mortar began with the burning of limestone in kilns to produce quicklime, a process that required careful control of temperature and timing to achieve consistent results. The quicklime was then slaked with water to produce lime putty, which could be stored for extended periods and actually improved with aging. Sand and water were added to the lime putty to create mortar with the proper consistency and strength characteristics for specific applications. Different types of mortar were formulated for different applications within castle construction. Foundation mortar required exceptional water resistance and strength to handle the loads and moisture conditions encountered below ground. Wall mortar needed good workability for easy application, combined with weather resistance and structural strength. Pointing mortar, used for finishing joints, required fine texture and good adhesion properties to create durable, weather-resistant surfaces.
The development of specialized mortar formulations represented centuries of experimentation and refinement that produced mortars optimized for specific construction applications and environmental conditions. Foundation mortars often incorporated pozzolanic additives, such as crushed pottery or volcanic ash, that improved water resistance and long-term durability in damp conditions. These additives reacted chemically with lime to create hydraulic mortars that could set and cure even underwater, providing superior performance in challenging foundation environments. Wall mortar formulations balanced workability requirements for efficient application against strength and durability requirements for long-term structural performance. The proportion of lime to sand affected both workability and final strength, while additives such as chopped fiber or animal hair provided tensile reinforcement that reduced cracking during curing. The consistency of wall mortar needed to support the weight of stone courses while remaining workable for efficient application and proper stone bedding. Pointing mortars for finishing exterior joints required formulations that provided superior weather resistance and appearance while maintaining good adhesion to existing mortar and stone surfaces. These mortars often used finer sand grades and special additives that improved surface texture and reduced water absorption. The application of pointing mortars required timing and technique that ensured good bonding with underlying materials while achieving smooth, durable surface finishes. Specialized mortars for specific construction applications included high-temperature mortars for fireplace and chimney construction, waterproof mortars for cisterns and water channels, and decorative mortars for architectural details and ornamental work. Each of these applications required unique formulations and application techniques that had been developed through experience with the specific performance requirements and environmental conditions involved. The production of lime for mortar required sophisticated kiln operations that could maintain proper temperatures for extended periods while processing large quantities of limestone efficiently. Lime kilns were typically constructed near limestone deposits to minimize transportation costs and were operated continuously during construction seasons to maintain adequate supplies of fresh lime for ongoing construction activities. The operation of lime kilns required specialized knowledge of fuel management, temperature control, and timing that ensured consistent lime quality. Quality control in lime production involved testing procedures that verified the proper burning of limestone and the resulting quality of quicklime produced. Underburned lime would not slake properly and would produce weak mortar, while overburned lime could create mortars that set too quickly or had poor working properties. Experienced lime burners could assess lime quality through visual inspection and simple tests that indicated whether the lime was suitable for different construction applications. The slaking process that converted quicklime to lime putty required careful control of water addition and timing to achieve proper texture and consistency for mortar production. Rapid slaking with large quantities of water could create heat that damaged lime quality, while insufficient water could result in incomplete slaking that left unreacted lime particles in the putty. The slaking process was often performed in specially constructed slaking pits that controlled the process while providing safe working conditions for workers handling dangerous quicklime. Aging and storage of lime putty improved mortar quality and workability through chemical and physical processes that occurred over time.
Aged lime putty developed improved plasticity and workability that made it easier to mix with sand and apply during construction activities. Storage systems for lime putty protected it from freezing and contamination while allowing for the aging process that improved its construction properties. Mortar mixing procedures required careful attention to proportions, mixing techniques, and timing that ensured consistent quality and performance throughout construction activities. The ratio of lime putty to sand affected both workability and final strength, while the amount of water controlled consistency and working time before the mortar began to set. Mixing techniques needed to achieve thorough blending without overworking the mortar in ways that could damage its structure and performance properties. Batch control systems ensured that mortar production could meet the demanding quantity and quality requirements of large-scale castle construction while maintaining consistent properties throughout extended construction periods. Standard measuring procedures and mixing protocols helped ensure that mortar properties remained consistent despite changes in workers, materials, and environmental conditions that occurred during long construction projects. The application of mortar required timing and technique that could only be learned through experience. Mortar needed to be applied when it had proper consistency for easy working, but before it began to set and lose its bonding properties. Workers used trowels, floats, and other specialized tools to spread mortar evenly and create joints that would provide maximum structural continuity and weather resistance. As walls rose higher, builders incorporated numerous specialized features that would serve defensive, structural, and practical functions throughout the life of the castle. Arrow loops, murder holes, and other defensive elements required precise construction to function effectively while maintaining the structural integrity of the walls. Doorways, windows, and passages needed careful framing and reinforcement to prevent weakening of the overall structure. The construction of towers represented some of the most challenging aspects of castle building, requiring all the skills and techniques used in wall construction, plus additional expertise in creating circular or polygonal structures that would provide maximum defensive effectiveness while efficiently using materials and space. Tower construction typically began with especially deep and robust foundations designed to support the concentrated loads imposed by tall, heavily built structures. Tower foundations required special engineering considerations that went beyond the requirements for wall foundations due to the concentrated loads and unique structural characteristics of these tall, narrow structures. The foundation system needed to distribute the enormous weight of stone towers across adequate soil areas while also resisting the overturning moments that could be created by wind loads or the impact of siege engines during military operations. Foundation designs typically incorporated wider bases and deeper footings than those used for walls, with special attention to soil conditions and drainage requirements that would ensure long-term stability. The transition from foundation to tower walls required careful construction techniques that ensured smooth load transfer while accommodating the geometric requirements of circular or polygonal tower shapes. This transition zone was often the most structurally critical part of the entire tower, requiring precisely cut stones and carefully planned construction sequences that would create strong, durable connections between foundation and superstructure.
The quality of workmanship in this transition zone often determined the long-term structural integrity of the completed tower. Circular tower construction presented unique challenges in stone cutting and fitting that required specialized skills and techniques not needed for straight wall construction. Each stone in a circular tower wall needed to be cut with precisely calculated curvature that would contribute to the overall circular geometry while maintaining structural strength and weather resistance. Master stonecutters developed templates and geometric techniques that enabled them to produce the precisely shaped stones needed for smooth, structurally sound circular construction. The construction of polygonal towers offered some advantages over circular designs in terms of stone cutting requirements, while still providing many of the defensive benefits of round towers. Polygonal shapes could be constructed using straight wall sections that were easier to build than curved walls, while the angled faces provided good defensive characteristics and efficient use of interior space. The corner connections between straight sections required special attention to ensure structural continuity and prevent weak points that could be exploited by attacking forces. Interior planning for towers required careful consideration of the multiple functions these structures would serve throughout the life of the castle. Towers typically contained multiple levels of rooms, storage areas, defensive positions, and circulation spaces that needed to be coordinated into efficient, functional layouts. The planning process needed to balance defensive requirements with habitability considerations while also accommodating the structural requirements of thick walls and the integration of stairway systems. The construction of spiral staircases within tower walls represented some of the most demanding technical challenges in medieval construction. Each step needed to be precisely cut and positioned to create safe, comfortable climbing surfaces while contributing to the overall structural strength of the tower. The central newel post around which spiral stairs were constructed required especially careful engineering to handle the concentrated loads from stair treads while providing stable support for the entire staircase system. Staircase construction techniques had been refined through centuries of experience with tower building to achieve remarkable precision and durability in these complex curved structures. The geometry of spiral staircases required mathematical calculations to ensure proper rise and run dimensions that would create comfortable, safe stairs while fitting within the space constraints imposed by tower wall thickness and interior layout requirements. Master craftsmen developed specialized techniques for laying out and cutting the precisely shaped stones needed for staircase construction. Tower wall construction proceeded using techniques similar to those employed for castle walls, but with additional attention to the structural requirements of tall, narrow structures that were subject to different load conditions and stability requirements. The thickness of tower walls often exceeded that of castle walls to provide additional structural strength and defensive capability, requiring careful planning of material quantities and construction logistics to handle the increased material requirements efficiently. Defensive features built into tower construction included arrow loops, murder holes, and other military elements that needed to be integrated into the structural design without compromising strength or creating weak points that could be exploited by attackers. These defensive features required specialized stone cutting and construction techniques to achieve the precise geometries needed for effective military use, while maintaining the structural integrity of the tower walls.
Tower walls were often thicker than castle walls and were built using the same composite construction methods but with additional attention to structural continuity and defensive features. The circular shape of most towers created special challenges in cutting and fitting stones, requiring skilled craftsmen who could create the curved surfaces needed for smooth, strong construction. Interior features of towers required careful planning and construction to provide the multiple levels of rooms, stairs, and defensive positions that made towers effective military and residential structures. Spiral staircases were built into the thickness of tower walls using carefully cut stones that formed both the structural support and the finished surfaces of these complex curved structures. The construction of staircases within tower walls demonstrated some of the highest levels of craftsmanship in castle building. Each step needed to be precisely cut and positioned to create a smooth, safe climbing surface, while contributing to the overall structural strength of the tower. The central newel, or supporting column, around which spiral stairs were built, required especially careful construction to handle the concentrated loads and provide stable support for the entire staircase system. As towers and walls neared completion, builders turned their attention to the complex systems of roofs, floors, and interior structures that would make the castle functional for its intended purposes. Wooden floor systems required careful engineering to span the wide spaces between walls while supporting the loads of people, furniture, and equipment that would occupy castle rooms. Floor construction typically used heavy timber beams that spanned between walls and provided support for wooden planking or stone paving that formed the finished floor surfaces. These timber beams needed to be carefully sized and positioned to handle the loads they would carry, while fitting properly into sockets and supports built into the castle walls during construction. Roof construction represented the final major phase of castle construction and required specialized expertise in timber framing, roofing materials, and weather protection systems. Castle roofs needed to shed rainwater and snow effectively while providing protection for the interior spaces and structural elements below. The design and construction of roof systems required careful attention to local climate conditions, available materials, and the architectural requirements of different parts of the castle. Timber framing for castle roofs used techniques that had been developed through centuries of experience with large wooden structures. Master carpenters created complex systems of rafters, purlins, and braces that would distribute roof loads evenly while providing stable support for roofing materials. These timber frames were often pre-cut and fitted in ground-level workshops, then raised into position and assembled using traditional joinery techniques that required no nails or metal fasteners. Roofing materials varied depending on local availability and the requirements of specific buildings within the castle complex. Clay tiles provided excellent weather protection and could be manufactured on site using local clay deposits. Stone slates were more expensive, but offered superior durability and fire resistance. Wooden shingles were less expensive, but required more maintenance and provided less fire protection. The installation of roofing materials required specialized techniques to ensure weather-tight construction that would protect the castle interior from moisture infiltration. Tiles and slates were laid in overlapping patterns that would shed water effectively while allowing for thermal expansion and contraction.
flashing and sealing systems around chimneys, gutters, and other roof penetrations required careful attention to prevent leaks that could damage interior structures or create unhealthy conditions. The design of roofing systems for castles required understanding of local climate conditions, material properties, and structural requirements that would ensure long-term weather protection and durability. Roof slopes needed to be calculated to provide adequate water shedding while supporting the loads imposed by roofing materials and accumulated snow or ice. The selection of roofing materials needed to balance cost, availability, durability, and fire resistance considerations that varied depending on local conditions and strategic requirements. Clay tile production for castle roofing often took place on or near construction sites, using local clay deposits and specialized kilns designed for tile manufacturing. Tile production required careful control of clay preparation, forming techniques, and firing temperatures to produce tiles with consistent dimensions and weather resistance properties. The forming process used wooden molds or other shaping devices to create tiles with proper profiles for effective water shedding and secure installation. Stone slate roofing required quarrying and preparation techniques that could produce thin, flat stones with consistent thickness and smooth surfaces suitable for roofing applications. Slate quarrying involved splitting stone along natural cleavage planes to create thin sheets that could be further shaped and sized for roofing use. The selection and preparation of slate required expertise in reading stone structure and using specialized tools to achieve the precise dimensions needed for weather-tight roof construction. Wooden shingle production used splitting and shaving techniques that converted timber into thin, overlapping pieces suitable for roof covering. Shingle production required selection of appropriate wood species with good weather resistance and splitting characteristics, typically cedar or other naturally rot-resistant species. The production process involved controlled splitting along grain lines, followed by smoothing and sizing to create shingles with consistent dimensions and weather-shedding properties. Installation techniques for different roofing materials required specialized knowledge and tools that ensured proper attachment and weatherproofing performance. Clay tiles required support systems and attachment methods that accommodated thermal movement, while providing secure installation that could resist wind loads and weather extremes. Stone slates needed drilling and fastening techniques that prevented cracking while providing reliable attachment to roof structures. Underlayment systems beneath roofing materials provided additional weather protection and helped prevent moisture infiltration through minor defects in the primary roofing system. These underlayments typically used organic materials such as treated fabric or specially prepared papers that could shed water while allowing vapor transmission that prevented moisture accumulation within roof structures. Flashing systems around roof penetrations, intersections, and edges required metalworking skills and specialized installation techniques that created watertight seals while accommodating building movement and thermal expansion. Lead was commonly used for flashing applications due to its malleability and corrosion resistance, though other metals were sometimes used depending on availability and cost considerations. Gutter and drainage systems collected and directed roof runoff away from castle walls and foundations to prevent water damage and maintain dry conditions around castle perimeters. These systems required careful sizing and installation to handle peak rainfall loads while maintaining proper slopes for effective water flow. Downspouts and drainage channels directed water to appropriate disposal areas that would not undermine foundations or create water accumulation problems. Ventilation systems integrated into roof construction provided air circulation that prevented moisture accumulation and maintained comfortable interior conditions, while also supporting proper operation of heating and cooking systems. Ridge vents, eave ventilation, and other air circulation features required careful design and installation to provide adequate airflow without compromising weather protection or structural integrity. Maintenance access systems built into roof construction enabled ongoing inspection and repair activities that were essential for long-term roof performance and castle protection. These systems included safe walking surfaces, anchor points for workers, and access routes that allowed maintenance personnel to reach all areas of complex roof systems safely and efficiently. Roof construction quality control involved inspection procedures that verified proper installation of all roofing components and systems before interior finishing work proceeded. These inspections checked for proper material installation, adequate weather sealing, and correct operation of drainage and ventilation systems that were critical for long-term building performance and occupant comfort. Throughout the construction process, builders paid careful attention to the numerous systems and features that would make the castle functional for daily life as well as effective for military purposes. Water supply systems included wells, cisterns, and channels that would provide reliable access to fresh water even during extended sieges. Waste disposal systems incorporated carefully designed latrines and drainage systems that would maintain sanitary conditions within the castle walls. The engineering of water supply systems required sophisticated understanding of hydraulics, geology, and construction techniques that would ensure reliable operation under all conditions. Well, construction involved drilling or digging through soil and rock layers to reach underground water sources, requiring specialized tools and techniques for excavation in confined spaces. The lining of wells with stone or timber prevented collapse and contamination while providing safe, convenient access to water supplies. Windlass systems and other mechanical devices enabled the efficient lifting of water from considerable depths using human or animal power. Cistern construction provided alternative or supplementary water storage that could maintain adequate supplies during periods when wells might be compromised or when siege conditions prevented access to external water sources. These underground storage chambers required waterproof construction techniques using specially formulated mortars and careful stone fitting to prevent leakage that could contaminate stored water or waste precious supplies. Cistern systems often incorporated filtration and settling chambers that improved water quality and removed sediment and debris from collected rainwater. The design of water distribution systems within castles required careful planning to provide convenient access to water throughout the complex while maintaining security and preventing contamination. Channels, pipes, and conduits needed to be constructed with materials and techniques that would provide long-term durability while resisting freezing, blockage, and deliberate sabotage during military operations. The routing of water systems needed to avoid interference with defensive systems while providing adequate capacity for both normal operations and emergency conditions. Waste disposal systems required equally sophisticated engineering to maintain sanitary conditions within castle walls while preventing the accumulation of wastes that could create health hazards or compromise defensive effectiveness. Latrine construction involved the creation of private and communal facilities that provided convenient access while incorporating ventilation and drainage systems that would minimize odors and health risks. The positioning of latrines needed to balance convenience with security considerations and drainage requirements. Drainage systems for waste disposal typically incorporated gravity flow designs that carried wastes away from castle living areas to disposal points that would not create health hazards or provide intelligence information to potential attackers. These drainage systems needed to function reliably under all weather conditions while resisting blockage, damage, and infiltration by hostile forces. The construction of drainage channels and pipes required careful attention to grades, materials, and maintenance access that would ensure long-term functionality. Kitchen facilities within castles required specialized construction to accommodate the large-scale food preparation needed to feed castle populations that could number in the hundreds during normal operations and might increase significantly during military emergencies. Kitchen design needed to balance efficiency and safety considerations with security requirements and integration with overall castle defense systems. The scale of kitchen operations required facilities that could handle food preparation, cooking, and storage for large numbers of people over extended periods. Fireplace and chimney systems in castle kitchens represented major construction undertakings that required specialized expertise in masonry, ventilation, and fire safety. Kitchen fireplaces were typically enormous structures, capable of accommodating whole animals for roasting and multiple cooking fires simultaneously. The construction of these fireplace systems required careful attention to structural support, fire safety, and smoke removal that would maintain safe, comfortable working conditions in kitchen areas while preventing fire hazards that could threaten the entire castle. Oven construction for baking and specialized cooking required additional masonry expertise to create structures that would provide even heating and efficient fuel use for bread production and other cooking requirements. These ovens needed to be integrated into overall kitchen designs while providing adequate capacity for the large-scale baking operations needed to supply castle populations with bread and other baked goods. The construction techniques used for oven building had been developed through centuries of experience with large-scale food preparation requirements. Storage facilities throughout castles needed to provide secure, convenient space for the enormous quantities of food, weapons, equipment, and supplies required for both daily operations and extended siege situations. Storage design needed to balance accessibility with security while providing adequate protection for stored materials from weather, pests, and theft. The construction of storage facilities required attention to ventilation, moisture control, and structural requirements that would ensure long-term preservation of valuable supplies. Granary construction required specialized techniques to protect stored grain from moisture, rodents, and insects while providing convenient access for regular use and inventory management. These facilities often incorporated raised floors, ventilation systems, and pest control features that had been developed through experience with long-term food storage requirements.
The design of granaries needed to balance storage capacity with preservation requirements and security considerations that would protect valuable food supplies during military emergencies. Armory construction provided secure storage for weapons, armor, and military equipment that needed to be readily accessible during military operations, while remaining protected from weather, theft, and sabotage during peaceful periods. These facilities required specialized construction techniques that would provide adequate security while maintaining convenient access for maintenance, inspection, and deployment of military equipment when needed. Kitchen facilities required specialized construction to handle the enormous fireplaces, ovens, and food preparation areas needed to feed the large populations that would inhabit the castle. These kitchen facilities needed proper ventilation to remove smoke and cooking odors while providing safe, efficient spaces for food preparation and storage. Storage facilities throughout the castle needed to accommodate the enormous quantities of food, weapons, tools, and other supplies required for both daily life and military operations. These storage areas required construction details that would protect stored materials from moisture, pests, and theft while providing convenient access for regular use. The completion of a castle construction project represented the culmination of years or decades of coordinated effort by hundreds of skilled craftsmen and laborers. The final phases of construction included the installation of doors, windows, and hardware that would provide security and weather protection for castle interiors. Decorative elements and architectural details were added to create the impressive appearance that demonstrated the wealth and power of the castle's owner. The installation of doors throughout the castle required specialized carpentry skills and custom hardware that would provide security, weather protection, and convenient operation under the demanding conditions of castle life. Door construction typically used heavy timber planks reinforced with iron strapping and hardware that could resist both forced entry attempts and the daily wear of constant use by castle inhabitants. The fitting of doors required precise measurement and adjustment to ensure proper measurement and adjustment to ensure proper operation while maintaining security and weather sealing capabilities. Window installation presented unique challenges in balancing defensive requirements with the need for natural light and ventilation in castle living spaces. Castle windows typically incorporated defensive features, such as iron bars or shutters, that could provide protection during military operations while allowing normal use during peaceful periods. The construction of window openings required careful integration with wall construction to maintain structural integrity while providing the precise geometries needed for effective window installation. Hardware installation throughout the castle required the services of skilled blacksmiths and metalworkers who created the custom hinges, locks, latches, and other mechanical components needed for doors, windows, gates, and other moving elements of castle construction. This hardware needed to provide reliable operation over decades of use while resisting corrosion, wear, and deliberate damage during military operations. The installation of hardware required careful fitting and adjustment to ensure smooth operation and long-term durability. Gate construction and installation represented one of the most critical aspects of castle completion, requiring specialized expertise in heavy timber construction, metalwork, and mechanical systems that would provide security while allowing convenient access during normal operations.
Castle gates typically incorporated multiple layers of protection, including heavy timber construction, iron reinforcement, and mechanical systems such as drawbridges and portcullises that could be operated quickly during military emergencies. Drawbridge construction required sophisticated engineering to create mechanical systems that could support the enormous weights of bridge structures while providing reliable operation under all conditions. The counterweight systems, pivot mechanisms, and control systems needed to operate drawbridges required precise construction and careful maintenance to ensure that these critical defensive systems would function when needed. The installation of drawbridge systems typically involved the coordination of carpentry, masonry, and metalworking trades to achieve proper integration with overall gate and wall construction. Portcullis systems provided additional layers of security that could be deployed quickly to block castle entrances during attacks or other emergencies. The construction of portcullis systems required specialized metalworking to create the heavy iron grating that formed the barrier, along with mechanical systems for raising and lowering these heavy structures quickly and reliably. The integration of portcullis systems with gate and wall construction required careful planning and precise execution to ensure proper operation without compromising structural integrity. The testing and adjustment of mechanical systems throughout the castle provided opportunities to identify and correct any problems before these systems would be needed for actual defensive operations. Gate mechanisms, drawbridges, portcullises, and other moving systems required careful testing under various load conditions to verify proper operation and identify any adjustments needed for smooth, reliable function. This testing process also provided training opportunities for castle inhabitants who would be responsible for operating these systems during military emergencies. Interior finishing work throughout the castle included the installation of floors, wall coverings, and other elements that would provide comfort and functionality for castle inhabitants while maintaining the defensive capabilities that were the primary purpose of these structures. Floor installation typically involved heavy timber construction that could span the wide spaces between castle walls while providing adequate support for the loads of people, furniture, and equipment that would occupy castle rooms. Timber floor systems required careful engineering to achieve adequate strength and stiffness while using the materials and construction techniques available to medieval builders. Floor joists needed to be properly sized and spaced to handle anticipated loads while providing adequate support for floor planking or other finish materials. The connections between floor systems and castle walls required special attention to ensure proper load transfer while accommodating the thermal expansion and contraction that could cause movement in large timber structures. Wall finishing techniques included plastering, painting, and other decorative treatments that would provide attractive, comfortable interior environments while protecting underlying masonry from moisture and other environmental factors. Plaster application required specialized skills to achieve smooth, durable surfaces that would provide good appearance and weather protection over long periods. The preparation of plasters using lime, sand, and other materials required knowledge of material properties and mixing techniques that would produce consistent, high-quality results. Decorative painting and other artistic treatments provided opportunities to demonstrate the wealth and cultural sophistication of castle owners while creating pleasant living environments for castle inhabitants.
These decorative treatments often incorporated heraldic symbols, religious themes, and other imagery that reflected the values and affiliations of the castle's owner. The execution of decorative treatments required artistic skills as well as technical knowledge of pigments, binding agents, and application techniques that would provide long-lasting results. Heating system installation throughout the castle required the construction of fireplaces, chimneys, and related systems that would provide adequate warmth during cold seasons while maintaining fire safety and structural integrity. Castle heating systems typically relied on wood-burning fireplaces that required substantial masonry construction and careful integration with overall building design to ensure safe, effective operation. The construction of chimney systems required specialized masonry techniques to ensure proper draft and safe operation while resisting weather damage and fire hazards. Defense systems received final attention during the completion phases, with the installation of gates, drawbridges, and mechanical systems that would control access to the castle during both peaceful and military periods. These defensive systems required precise construction and careful testing to ensure that they would function effectively when needed while providing convenient access during normal operations. The landscaping and site development around the completed castle required additional months or years of work to create the approaches, gardens, and supporting structures that would complete the castle complex. Roads and bridges needed to be built or improved to provide proper access to the castle while maintaining defensive advantages. Gardens and agricultural areas within the castle walls or nearby provided fresh food and pleasant surroundings for castle inhabitants. Water systems required final connections and testing to ensure reliable operation under all conditions. Wells needed to be properly sealed and equipped with lifting mechanisms that would provide convenient access to fresh water. Drainage systems required final cleaning and adjustment to ensure proper operation during heavy rainfall or other challenging conditions. The testing and commissioning of completed castle systems provided opportunities to identify and correct any problems that had not been apparent during construction. Defensive systems were tested to ensure proper operation and to train castle inhabitants in their use. Water systems were tested under various load conditions to verify their capacity and reliability. Structural elements were inspected to identify any problems that needed correction before the castle was occupied. The final completion of a castle construction project marked not just the end of a building process, but the beginning of a new phase of life for the structure and its inhabitants. Castles were built to last for generations, and their completion represented an investment in the future that would provide security, prestige, and functionality for decades or centuries to come. The knowledge and techniques used in castle construction represented the accumulated wisdom of generations of builders who had refined their methods through experience with countless projects across Europe and beyond. Each castle construction project added to this body of knowledge and contributed to the development of building techniques that would influence architecture and engineering for centuries to come. The social and economic impact of castle construction extended far beyond the immediate construction site and participants. These massive projects provided employment for hundreds of workers and created markets for materials and supplies that supported entire regional economies. The skills and techniques developed during castle construction were applied to other building projects, contributing to the overall development of construction technology and architectural capabilities. The legacy of medieval castle construction can be seen today in the magnificent structures that continue to dot landscapes across Europe, and in the construction techniques and architectural principles that evolved from this remarkable period of building activity. The precision, durability, and beauty of these structures continue to inspire architects and engineers who study the methods used by medieval builders to create such impressive and lasting works of architecture. The influence of castle construction techniques extended far beyond the immediate military and residential purposes for which these structures were originally built. The engineering principles developed through castle construction contributed to advances in bridge building, cathedral construction, and other major architectural achievements of the medieval period. The organizational systems developed for managing large-scale construction projects provided models for other complex undertakings that required coordination of multiple trades, materials, and logistics over extended periods. The preservation and restoration of medieval castles in modern times has provided valuable insights into historical construction techniques, while also contributing to our understanding of medieval society, technology, and culture. Archaeological investigations of castle sites have revealed details of construction methods, material sources, and building sequences that help us appreciate the remarkable achievements of medieval builders. Conservation efforts have developed new techniques for maintaining and restoring ancient masonry while preserving the historical authenticity and structural integrity of these important cultural monuments. Modern construction technology has built upon many of the fundamental principles first developed during the medieval period of castle construction. Concepts such as composite wall construction, structural load distribution, and systematic quality control continue to influence contemporary building practices. The attention to material selection, construction sequencing, and long-term durability that characterized medieval castle construction provides lessons that remain relevant for modern architects and engineers facing similar challenges with different materials and technologies. The economic and social systems that supported castle construction demonstrated sophisticated approaches to project financing, labor organization, and resource management that provide insights into medieval economic development and social organization. The ability to mobilize and sustain the enormous investments of labor, materials, and financial resources required for castle construction reflected the development of complex economic and political systems that could support long-term, large-scale projects requiring coordination across multiple communities and regions. The technological innovations that emerged from castle construction projects contributed to broader advances in metallurgy, masonry, carpentry, and other crafts that benefited society well beyond the immediate construction industry. Improvements in tool design, material processing techniques, and construction methods developed for castle building found applications in other types of construction and manufacturing activities that contributed to overall economic and technological development during the medieval period.
Educational systems that developed around construction trades provided models for technical education and skills development that influenced the growth of professional guilds and apprenticeship systems throughout medieval Europe. The transmission of knowledge and skills from master craftsmen to apprentices ensured continuity of technical expertise, while also providing mechanisms for innovation and improvement in construction techniques and standards. The international exchange of construction knowledge and techniques that occurred as builders and craftsmen traveled between different castle projects contributed to the spread of architectural styles, engineering innovations, and construction technologies across national and cultural boundaries. This exchange of knowledge helped establish common standards and practices that enabled the remarkable consistency and quality achievements that characterize the best examples of medieval castle construction. The documentation systems that developed during major castle construction projects, including drawings, specifications, and records of material quantities and costs, provided early examples of project management and technical documentation practices that would later evolve into modern engineering and architectural practices. These documentation systems also provide modern historians and archaeologists with valuable sources of information about medieval construction practices and technological capabilities. The environmental considerations that influenced medieval castle construction, including site selection, material sourcing, and construction techniques adapted to local climate conditions, demonstrated understanding of sustainable building practices that remain relevant for contemporary construction projects. Medieval builders developed techniques for working with local materials and environmental conditions that minimized transportation costs and environmental impacts while achieving excellent long-term performance. The maintenance and repair traditions that developed around medieval castle construction established principles of building conservation and ongoing care that helped ensure the survival of these structures through centuries of use and changing conditions. These maintenance practices provide models for contemporary conservation efforts while also demonstrating the importance of ongoing care and attention in achieving long-term building performance and durability. Cultural and artistic achievements represented in castle construction demonstrate the integration of functional and aesthetic considerations that created buildings serving practical purposes while also expressing cultural values and artistic vision. The decorative elements, proportional relationships, and overall design approaches developed for castle construction influenced broader artistic and architectural developments that contributed to cultural achievements extending far beyond military architecture. The strategic and military innovations that drove castle construction also contributed to broader developments in military engineering, fortification design, and defensive planning that influenced military architecture and strategic thinking for centuries. The defensive concepts and construction techniques developed for castle building provided foundations for later developments in military engineering that continued to evolve as military technology and strategic requirements changed over time. Modern visitors to medieval castles can appreciate not just the final results of these construction projects, but also the remarkable achievement they represent in human organization, technical skill, and artistic vision. Every stone in these walls represents the work of skilled craftsmen who took pride in their contribution to structures that they knew would outlast their own lives and serve future generations.
The story of how castles were built is ultimately a story about human ambition, creativity, and determination. These projects required vision to imagine structures of such scale and complexity, skill to execute construction with the tools and techniques available, and persistence to continue work through the years or decades required for completion. The builders who created these magnificent structures left us not just impressive buildings, but also examples of what can be accomplished when human knowledge, skill, and determination are focused on worthy goals. As we reflect on this remarkable period of construction achievement, we can appreciate both the specific technical accomplishments of medieval builders and the broader lessons their work provides about the importance of craftsmanship, planning, and long-term thinking in any significant undertaking. The castles they built continue to stand as monuments to their skill and dedication, and their construction techniques continue to influence building practices today. Heating system installation throughout the castle required the construction of fireplaces, chimneys, and related systems that would provide adequate warmth during cold seasons while maintaining fire safety and structural integrity. Castle heating systems typically relied on wood-burning fireplaces that required substantial masonry construction and careful integration with overall building design to ensure safe, effective operation. The construction of chimney systems required specialized masonry techniques to ensure proper draft and safe operation while resisting weather damage and fire hazards. The design of castle heating systems required understanding of heat distribution principles, combustion requirements, and safety considerations that would provide effective heating while minimizing fire risks and fuel consumption. Fireplace design needed to balance heat output against safety requirements while providing adequate draft for proper combustion and smoke removal. The sizing and positioning of fireplaces throughout castle interiors required careful planning to provide adequate heating coverage while minimizing construction costs and maintaining structural integrity. Chimney construction represented some of the most technically demanding masonry work in castle construction, requiring specialized skills and techniques that ensured proper operation and long-term durability. Chimney walls needed to be constructed with fire-resistant materials and techniques that could withstand high temperatures and thermal cycling without cracking or deteriorating. The internal surfaces of chimneys required smooth finishes that would promote good draft while resisting creosote accumulation and fire hazards. Draft systems in castle chimneys required careful design and construction to ensure adequate airflow for proper combustion while preventing smoke infiltration into living spaces. The height, cross-sectional area, and internal configuration of chimneys needed to be calculated to provide appropriate draft characteristics for the fireplaces they served. Multiple fireplaces, sharing common chimneys, required complex internal configurations that prevented interference between different heating systems. Fireplace construction required specialized masonry techniques that created efficient, safe heating systems while integrating properly with overall castle construction. Fireplace foundations needed to support the enormous weight of masonry construction while providing proper insulation from surrounding structural elements. The construction of fireplace openings required precise stonework that created proper proportions for efficient combustion while providing attractive, functional heating systems.
Fuel storage and handling systems throughout castles required specialized construction to provide adequate capacity for heating fuel while maintaining convenient access and fire safety. Wood storage areas needed to be positioned for convenient access to fireplaces while being protected from weather and separated from living areas to reduce fire risks. The design of fuel storage systems needed to balance capacity requirements against space constraints and safety considerations. Ventilation systems, integrated with heating systems, provided fresh air circulation that supported proper combustion while maintaining comfortable interior air quality. These systems required careful design to provide adequate airflow without creating uncomfortable drafts or compromising the efficiency of heating systems. The integration of ventilation with heating systems required understanding of airflow principles and careful attention to the interaction between different building systems. Safety systems for castle heating included fire prevention measures, emergency procedures, and construction details that minimized fire risks while providing effective heating capabilities. Fire-resistant construction materials and techniques reduced the risk of structural fires, while proper maintenance procedures ensured that heating systems remained in safe operating condition throughout their service lives. Emergency access and firefighting capabilities provided additional safety measures that could respond quickly to heating-related incidents. The testing and commissioning of heating systems provided opportunities to verify proper operation and identify any adjustments needed for safe, efficient performance. Initial testing of fireplaces and chimneys checked for proper draft, adequate heat output, and safe operation under various conditions. These tests also provided training opportunities for castle inhabitants who would be responsible for operating and maintaining heating systems throughout the castle's operational life. Maintenance procedures for castle heating systems required ongoing attention to cleaning, inspection, and repair activities that ensured continued safe operation and optimal performance. Chimney cleaning removed creosote and debris that could create fire hazards or reduce draft efficiency. Fireplace maintenance included inspection and repair of masonry components, replacement of worn hardware, and verification of proper operation for all heating system components. The integration of heating systems with other castle systems required careful coordination to ensure compatibility and optimal performance of all building systems. Heating systems needed to work effectively with ventilation systems, water supply systems, and structural systems without creating conflicts or compromising the performance of any individual system. This integration required comprehensive planning and ongoing coordination throughout the construction process. Documentation systems for heating system construction provided records of design specifications, construction details, and operational procedures that supported both construction quality control and long-term maintenance activities. These records included drawings, material specifications, and testing results that could be referenced during maintenance activities or future modifications to heating systems. Quality assurance procedures for heating system construction involved inspection and testing activities that verified proper installation and safe operation of all heating system components. These procedures checked for proper material installation, correct construction techniques, and compliance with safety requirements that were essential for reliable, safe heating system performance throughout the castle's operational life. Environmental considerations in heating system design included efficiency measures that minimized fuel consumption while providing adequate heating performance. These considerations involved fireplace design optimization, chimney performance enhancement, and fuel management strategies that reduced environmental impact while maintaining comfortable interior conditions throughout castle living spaces. The completion of heating system installation marked a critical milestone in castle construction that enabled year-round occupancy and comfortable living conditions for castle inhabitants. Properly functioning heating systems provided the thermal comfort necessary for productive castle operations, while also supporting the health and well-being of residents during harsh winter conditions that characterized much of medieval Europe. And so, as we reach the end of our exploration of how these magnificent fortresses came to be, from the initial surveying of windswept hilltops to the final installation of warming hearths that would sustain generations of inhabitants, we're left with a deep appreciation for the countless hands, minds, and hearts that went into their creation. And with that sense of wonder at human achievement, I bid you good night.